root mean square value of alternating current. Okay, we have seen before that this alternating current, when you represent it, you know, diametrically or graphically, you will get a graph like this type. Okay, so this wave here, it is a one complete wave, and the time taken to complete one cycle, it is known as time period, and for that we denote by capital T. Half of the time period, it will be T upon 2. So at this point, at this time 0, T by 2 and capital T, the current is always 0. Okay, now when we talk about the average value of AC current, so the average of AC current in this case will be 0. Why? Because the current in the upper half cycle will cancel with the current in the negative half cycle. So that is why we have average value of AC current to be equals to 0. Or that can be easily viewed from here also, because this is the mid value. So the mid value of current means the average value. So the average value automatically right here, it is equals to 0. Alright. Now let us calculate the electric power. The electric power, it is given by this formula, I square R. This I here is the average value. But for an alternating current, the average value is 0. So when the average value is 0, it means here that the electric power of the alternating current will be 0. So if the electric power of the alternating current is 0, then this will contradict to what we observe in our everyday life. Okay, at home, you always have an electric current. That means you always have electric power. So, but if the average value is 0, then how do you get that electric power? The electric power must be 0. Alright? So then, that problem, to calculate the electric power, it is now using, instead of average value, we are using another term, that is root mean square value. So with this root mean square value, instead of average value, you substitute by the root mean square value, then you will get the electric power supply at home. Okay, so this root mean square value, it is denoted by I with a subscript V, and it is defined as like this root mean square value is equivalent to the DC value or the DC current, in which when it flow for some resistance, let's say R, it would produce the same amount of heat as produced by the AC current when flow for the same resistance and for the same time. That is the definitions of root mean square value. Okay, now let us derive about the relation between the root mean square value and the peak value of alternating current. Okay, suppose this is my resistance and I connect this resistance to an alternating source. Okay, the instantaneous current which is produced by this alternating source of EMF E, let's say it is I. And this instantaneous current, if you remember, it is written as I equal I naught sine omega t, where I naught is the maximum value of the alternating current, omega is the angular frequency of the alternating current. Alright, so because this current here, it is passing through this resistor, so some heat will be produced across this resistance R. Suppose the current, let's say it is passing through this resistance R for a small time dt. Then you know from Joule's law that the amount of heat produced will be I square RT. Okay. But if you imagine that this current is passing through this resistance R for a small time dt, then the amount of heat that will be produced in this resistance R will be small. And that small heat is written as dH. And following this equation, I can say dH is equals to I square R and the time is dt. Or I can say dH is equals to, instead of I, you write I naught sine omega t. So with this square, it becomes I naught square sine square omega t and then R dt. So this is the small heat which is produced in the resistance R for a small time dt. Now the total heat produced in the resistance R over one cycle. Okay, when I say one cycle, it means the time varies from 0 to capital T, because we know T is the time taken to complete one cycle. So the total heat which is produced in this resistance R in one complete cycle can be obtained by integrating this equation. So if you integrate dH, you will get H. And integrate right hand side from 0 to capital T. You'll get like this. Okay. Or H is equals to, taking this I naught square outside, R outside because they are constant. So you integrate only sine square omega t dt. Or this heat which is produced in the resistance R can be written as H equal I naught square R, and I will change this sine square omega t to 1 minus cos 2 omega t by 2 and then dt like this. So we get this from the trigonometric formula only. Again, H is equals to I naught square R. Now this 2 I'll take it here and you split this integration. 1 into dt will be dt. Next, integrate from 0 to t cos 2 omega t dt. And these should be inside this bracket. Okay. Alright. Okay, I have to rub because I have a very little space over here. So please take a screenshot so that you will get the full calculation. You can see the full calculation. Okay. Now, let me let me write in this part. So this heat H is equals to I naught square R upon 2. If you integrate dt, you will get t. And the limit is from 0 to capital T. Integrations of cos 2 omega t, it will be minus sine 2 omega t upon 2 omega. Okay. And the limit is from 0 to capital T. Next, H is equals to I naught square R upon 2. Now, if you substitute the limits of integration, instead of small t, the upper limit is capital T. And you subtract it by substituting with the lower limit, then you'll get only just capital T. So this minus with minus, if you multiply, you'll get plus. And here again, I will substitute the limits of integration. Instead of small t, I'll write capital T. And this one, it becomes sine 2 omega. Instead of small t, the lower limit is 0. And then upon 2 omega. Okay. H is equals to I naught square R by 2 capital T plus. Okay. Now, 0 into 2 omega will be 0. So this term will disappear. Next, you'll have just sine 2 omega t upon 2 omega like this. Okay. Again, this H is equals to I naught square R 2 capital T plus. Now what is this omega? This omega is equals to 2 pi f. Omega is the angular frequency and f is the linear frequency, and the relations between them is this. Or this omega is equals to 2 pi, instead of f I'll write 1 upon t, which is the reciprocal of the time period. Or it means 2 pi upon t. Alright, so instead of omega I'll write 2 pi upon t times t upon 2 omega like this. So this t with this cancel, so h is equals to I naught square r upon 2 t plus. Now 2 into 2, 4. 4, that means sine 4 pi. So sine 4 pi is 0. So 0 upon 2 omega will be 0. So next you will have the amount of heat which is produced in that resistance capital R over one complete cycle. It is equals to I naught square R T upon 2. So this is the heat which is produced in this resistance capital R when the current I is passing through this R. Okay. Now, if IV is my root mean square value, then the heat which is produced in this resistance capital R over one complete cycle, if you use the current as IV, if you imagine that the root mean square value is IV, then we know IV is like a direct current only. So if it is a direct current, then the heat produced will obey the Joule's law, right? It will take that Joule's law equation, which is I square RT. But in this case, I is IV, which is the root mean square value. Okay, so this is my equation number 2. So if you compare this equation 1 and equation 2, you found that the left hand side of the two equations are equal. So therefore the right hand sides of these two must be equal. So I'll write from equation 1 and equation 2, you will get IV square RT is equals to I naught square RT upon 2. R from the left, R from the right cancel, T from the left, T from the right cancel. Again I have to rub. Or IV square is equals to I naught square by 2. And if you remove the square, then you'll get root over I naught square upon 2, or just IV is equals to I naught upon root 2. Okay, so this is the relation between the root mean square value and the peak value of the alternating current. Alright, now in a similar way you can calculate or you can show by yourself about the relations between the alternating EMF and the peak value of the alternating EMF. So the root mean square value of the alternating EMF is EV, and this EV should be equals to E naught by root 2. Okay, this is my equation 3, this is my equation 4. Alright, now this root 2, it means when you divide the numerator by root 2, you'll get 0.7, okay, into I naught. Okay, if you convert into percentage, then you'll get this is 70% of I naught. Okay, 70% of I naught. So what does it mean? It means here that if I naught, let's say, is equals to 10, okay, let me say 100 milliampere, then the root mean square value will be 70% of this, which means 70 milliampere. Okay, so in the graph, we have this is the graph of the alternating current. So in this graph, this is the peak value, and this value, it is I naught is equals to 100 milliampere. The root mean square value is just 70, it means it is smaller than this. So let's say it is somewhere here. So this is IV and this is equals to 70 milliampere. Okay, so it is this 70 milliampere which actually produce the same amount of heat, or which is equivalent to the direct current, and so it produces the same amount of heat as produced by the DC current when it flow for the same time in the resistance. Okay, all right. So similarly, for this alternating voltage, for the root mean square value of the alternating voltage, we can write EV is equals to 70% of E naught. All right. Okay. So what is the importance of this root mean square value? The importance of this root mean square value is that suppose in the in the domestic AC supply, suppose in any domestic AC supply, it is written as 230 volt 50 hertz. I think you might have seen, right, in any electrical appliances, whether it is your electric bulb, whether it is your electric heater or any appliances, you will always find you know this these types of number, which mean this 230 mean it's the potential or the EMF, and this 50 hertz it is the linear frequency. Okay, so when this AC supply it is written in this way, then this number 230 volt here, it is actually the alternating value, or we can say it is EV. So EV here means 230 volt. And let's say if it is also written that the current is 2 ampere, so this 2 ampere current, it doesn't mean alternating current, but it means the root mean square value, that is 2 ampere. So this is the important, when we say the alternating current is 2 ampere, it always means the root mean square value. When I say the alternating voltage of the AC supply is 230 volt, it always means the alternating value. Okay, so this is how the alternating values are related with the maximum value of the alternating currents and voltage. Okay, so I hope this topic is clear, and we shall continue in the next video.